the academia insight talk, and this is a APNet tradition and landmark session that we have very experienced researchers from academia to share their insight about the research. And we will have 4 speakers. The first speaker is Professor K.K. Ramakrishnan. Very briefly speaking, Professor K.K. is a distinguished and very respected professor from UC Riverside. And he is very senior. He graduated in 1983 before most of you were born, okay? Over the past...
Okay, yeah. I'm old.
Yeah. Okay, over the past 40 years, he made significant contributions to computer and communication networks. Okay, very brief. He will be talking about serverless computing today. Okay, let's welcome.
Okay. We've been working on serverless computing for a while now. Actually, I got started with Dan Lee's student who came and visited us in 2018-19. And we haven't let go. We still seem to be doing little things with it. And Kai says, give insight. I don't know how to give insight. So what I'm going to do is give you a little bit of what we've been doing. Some of it I've already talked about at SIGCON last year. I will very quickly touch upon it, and then afterwards try to give you a little bit more of the work that we've done since then. So this is not anything new to all of you. Even if you're doing the new fad of ML, you're probably still doing the same kind of thing, which is building applications that are built out of microservices. And that's how we are building cloud applications a lot now. And there's a great deal of benefit from that, which is the flexibility that comes for software developers to be able to independently develop and then deploy, test all of that of simple, small services, and then build them together to scale out. That has actually led to a lot of the work in the cloud service offering that people have with serverless computing. And, you know, it's really the main thing with this function as a service model is the characteristic that it is event-driven, more or less stateless, and short-running. And the main benefit from users is that, number one, the user doesn't have to deal with anything other than his application code. They're not looking to configure any of the core tasks that the cloud service provider has to do. So provisioning, managing the infrastructure becomes the responsibility of the cloud service provider. And you know, it also helps somewhat to remove this traditional always-on functionality that you have to have in a cloud service that people tend to do without a function as a service model. So users just develop only the function code, and everything else is taken care of by the cloud service provider. That function code is primarily running as a stateless event-driven component, and everything else is managed by the cloud service provider. So the user only pays as you go for processing those events. I'm going to take one example because that's the one that we've been working with for ages, but my belief is that that's no different than most of the other serverless offerings, which is that you've got a data plane and a control plane. The formatting is broken up a little bit. I think that's the difference between using, this is a Mac too. Anyway, so you have requests coming in, and it comes into an ingress gateway. that ingress gateway basically terminates the request. It's usually a HTTP request coming in. It's a REST API, and that ingress gateway then does all of the authentication authorization, and then decides, okay, now I'll look at the payload and decide what is the function that has to be invoked. And if that function invocation is done by getting it to a message broker, that message broker then says, well, I will figure out which function that request is initially destined to. If it is not running, then it works with the control plane to instantiate one. If it is running, then you send it to that function pod. That function pod has a couple of components, usually a sidecar, which is acting as a proxy, and that proxy then does a bunch of functions for that request, in addition to monitoring, collecting metrics, and so on, forwards that function to the user container. And if there's a chain of functions, then you go from one function to the next, and that interfunction networking is also done by a message broker. Metrics that are collected go up to the control plane. The control plane is responsible for instantiating containers for those functions and deciding when they are no longer active, terminating them, and so on. And then auto-scaling depending on the load, dealing with placement in the data center, and so on. I've talked about this before in terms of the overheads that are involved. I wanted to skip through that. You can look at old papers from SIGCOMM 2022. The main thing is, what are the things that we end up seeing with especially interfunction networking is a tremendous amount of overhead. The reason we get that overhead is because it's all been built with expediency in mind to pull things together as quickly as possible. And you've got a lot of kernel protocol processing, data copying, context switches, interrupts, and so on that you have to deal with. And the other thing is that the work of monitoring, maintaining health, and so on requires stateful, constantly running components in the user space. That is the responsibility of the crowd service provider rather than the function container. So there's this container-based sidecar, the message broker, and the ingress gateway. All of those have to be running constantly. So when we look at the fact that it is a serverless environment, there's still a bunch of serverful tasks that have to be maintained. And we said we want to deal with both of these and look at how to mitigate those penalties. So the first thing that we did in our SPRIGHT work was to say, well, let's look at that sidecar. It's basically dealing with events. And so we can actually look at how to make that truly event-driven rather than running constantly. And one of the nice things that we found, well, found is a word I shouldn't be using because we've been all working with BPF since you were not born. My first work with BPF was in the early 80s. And we've been working with that. But eBPF has been now resurgent, and that has been used for a number of event-driven tasks. And we said, why not use it for the sidecar? So we've built a eBPF sidecar. A bunch of people are using that now. And we see that the message broker is basically a forwarding engine in some sense, an application-level forwarding engine. And that can also be a eBPF-based message broker. And so what we ended up doing was removing a lot of the constantly running tasks by using eBPF. The other thing that we've been preaching for many, many years now is to say, look, if you have components that are running on the same node, why not take advantage of the memory that is there and you use shared memory? We've been using shared memory for NFV for a while, and we found that we can do the same thing here, not necessarily always using DPDK, but shared memory. There are many ways of doing interfunction networking by having that data that is coming in go into a shared memory pool and then having that in its final resting place for you to be able to share across functions. So the enhancements that we did was to say, well, let's figure out how to use eBPF to replace all these constantly running components. Okay? And the second was to use the shared memory to reduce data movement overhead. And ultimately, the last one was to make sure that we get rid of the message broker. There's a bit of state that has to be maintained, and what we do is use the kernel's eBPF map to keep the routing state so that we can then do direct function routing. The benefit of all that is that for all the work that you do within the chain, we get rid of most of the overheads in terms of the amount of protocol processing, the number of context switches, copies, all of that goes away. And if you look at what happens in a typical microservice deployment using serverless, we get 5-6 times better throughput. If you look at the tail latency, looking at the 95th percentile, we get almost 50 times better than the traditional sort of kernel-based networking. And even compared to a constantly running serverful gRPC-based offering with just microservices, which you're burning CPU, even compared to that, we're able to do an order of magnitude better in terms of latency because of getting rid of a lot of the kernel user space boundary crossings. And all of that we can do with about 10% of the CPU consumption. Okay? So this is old work. We were quite proud of it. And then we said, well, can we do better? And that's what I'm going to be talking about today. One of the things that we were saying before was, with this approach, we can sidestep some of the penalties that you typically see in serverless computing, which is this cold start penalty. Because if you're doing everything purely event-driven, you can afford to keep it running. But of course, that means you're profligate in using memory. And so we said, can we do better? So one of the things that you see with even our approach is that the amount of time that we have to spend in starting up a container in this container-based approach doesn't go away. Everything else goes away, but that startup latency is still there. And so even though we don't have that much expense because of this eBPF sidecar and the broker and so on, there is still that startup latency. And if you're not going to be able to have such a large number of containers running in the sense of not consuming CPU but still in memory, then you need to find a way of mitigating that. And we said, hey, we can do better. I'm really, really sorry. I checked it out and it looked right, but it doesn't look right now. Formatting. If we look at starting up a Docker container versus starting up a unikernel, this is not new. We looked at a whole bunch of unikernels that exist, and the startup latency is dramatically lower. So we said, can we use that? Yes, but there are things that we have to solve. So let me actually just first talk a little bit about the performance improvement and the concerns that come up with using unikernels. The first one is it's a single address space. Okay? And think about what we needed to do. We needed to have that sidecar. We need to be careful because that is something that the cloud service provider depends on for being able to be sure that they provision, manage resources properly. So if you now have a single address space unikernel, then you have to make sure that all of those components are trusted. The other is that even though we've been talking about shared memory for the last 10 years, the constant harassment from everybody is that, hey, it is not really safe, okay? Because there is a potential conduit for leakage, data leakage and corruption, and it may be caused just by simple bugs rather than malicious behavior. And so we said we need to deal with that sharing concern. Couple of aspects. One is intra-unikernel, that is between user function code and all of the libraries that the OS depends on and the cloud service provider depends on. And the second is when you go between unikernels and you're having functions using that shared memory, you want to make sure that that's also safe. So long ago, we said, let's look at how to protect that. And Marco was saying, hey, you should look at using SGX. It's heavyweight. And we sort of hesitated for many years to adopt that. And also, one of the other things is that the shared memory processing that we have is limited to a single node. And what we ended up having to do, going across nodes, is doing all this data copy, going from one gateway to the other node's gateway. So there was that price to pay as well. So we said, can we take care of those? And then the final thing is eBPF depends on the kernel. So if you're going to use unikernels in a single address space, then that really doesn't lend itself to using eBPF, so we needed to find an alternative. So those are the things that we did in our work called SURE, which is to look at how to address each one of these problems. So if you look at a worker node, you've got multiple user functions, and those might or might not trust each other. And we look at using shared memory across those user functions. And there are components that are running inside that unikernel, which is doing the tasks that a sidecar would do. So what we ended up doing was to say, can we build a eBPF-like sidecar, a library-based sidecar that runs in the unikernel? And can we also extend the zero-copy networking to go across nodes? We hadn't looked at RDMA yet, but we have since then. But we started off by looking at a user space protocol stack. Tencent had this F-stack that they released, so we picked it up. And then we said, we can customize it to be truly zero-copy, and we called it Z-stack. We used that to help in doing zero-copy transfers between nodes. Then we said, how are we going to protect these components? So we started looking at using MPK. That's something that Intel has as a memory protection key instruction. Very efficient, a lot simpler to use than SGX. And so that's what we've been looking at to secure both the components within the unikernel that we want to protect as part of the trusted computing block, as well as securing the shared memory so that we can still retain high performance. I want to give you one little performance thing before I get to talking a little bit more in detail about how we use MPK. So if you look at the sidecar itself, it does a bunch of things in terms of dealing with metrics handling, traffic filtering, rate control, and all of that. And we built that as a library, okay, so that it can be linked to function code within the unikernel. And so the sidecar has a sequence of these handlers that the cloud service provider depends on. And by having this in the unikernel, that sidecar can now be very efficiently invoked, simple function calls, and it takes care of, all of the sidecar container overheads that we saw before. So if you look at the performance with that library-based sidecar compared to, let's say, NGINX, it's dramatically lower in terms of CPU consumption, latency, and when we look at throughput, in fact, this library-based sidecar almost is as efficient as not having a sidecar at all. So we said, how are we going to provide all of this protection, and how do we do this with MPK? So if you look at what we have as the trusted computing base in this unikernel, we want to, of course, protect the hypervisor and all its tool chains, and all the unikernel modules, whether it is the scheduler, the booter, the network I/O, library, all of that. So the trust model that we have, which I think is reasonable, is that the user trusts the infrastructure, but the infrastructure does not trust the user. There's other things that you can do for users to validate what the infrastructure is doing, but that's a separate issue. So we say we want to be careful because user code could be just buggy because you're writing functions that anybody can run on your infrastructure. And one of the things that we believe is that functions within a chain inevitably have to trust each other. So we started off in the past by talking about having a secure domain, but we now look to see how to enhance that. So if you look at the kind of isolation that we provide, you've got a bunch of functions in one secure domain, okay? And then we use MPK to provide memory level isolation in the shared address space. So the shared memory between functions is protected using MPK. And that sandbox itself of untrusted user code within that single address space will be protected so that if you have components that are running that the cloud service provider depends on, those are also protected within that unikernel. So I wanted to give a little bit of a tutorial on MPK. This is not, I don't work for Intel, but that helps me to understand how we use it and how to use it carefully, because you can't just use it blindly. So this is an instruction that you have, and it's associated with page table entries in Intel server CPUs. And there is a MPK register. It's a protection key register, and it's a 32-bit register. And basically, what you have is one for every CPU core, okay? And you basically have 2 bits for each key. It can be either, completely disable access, or it can be read-only, that is write disable, okay? And you've got, essentially out of the 32 bits, you've got 16 different keys. Okay, so those 16 keys give you that kind of capability to say read-only, read-write, or no access. And what you end up doing is having a 4-bit entry for each page table entry to point to one of these keys. Okay? Might be view it as being severely limiting because you say, well, I've got a key, I've only got 16 keys, how do I manage that? So you've got to manage that carefully, and that's what we've done. Okay? So you can have different page table entries point to different keys, and if you want to change access, what you end up doing is potentially directly writing to that PKRU register. Okay? So the simple thing would be to say, well, I will have update to the PKRU register, but then there are only 16 pages, and that's not enough. But we actually are careful in how we use MPK. We split it into two very carefully thought out ways of splitting it. One is to write data to the PKRU. So that's just a single instruction. And that is okay for very limited fast access. And so we use that for the unikernel's trusted computing block components, okay, by updating the register. So you can basically say that I can go from read-only to read-write access or disable access to a particular page table entry by directly writing to that PKRU register. That's okay for fast coarse-grained updates, but for the shared memory, what we say is, rather than doing that, we'll update the page table entry to point to a different entry in the PKRU register. Okay? So we've got these 4 bits. So for things that are larger scale, but we can afford to be more fine-grained, we basically update the page table entry. There is a price to pay, which is that the TLB misses means you have to flush the TLB after you update that key ID in the page table entry. But it allows for much more scalable access. So by doing the split for shared memory buffers, we manage it using this page table entry update. And then for the TCB components, we use this coarse-grained but faster update directly into the PK register. Okay? So that's the sort of basic key that the CPU gives us. Now, how do we control that key? Because anybody can write to that, right? Especially if you give user functions the ability to update that PKRU register. So what we say is, instead of that, we're going to have an API, so we create a call gate abstraction, basically an API, so that user code can safely interact with these protected pages. Okay? So what we do is to say that when you're writing to the PKRU or the page table entry update, we go through a call gate. So we can look at function code. Binary inspection, we don't need to get to the source code of the function. And we can say, well, let's make sure that there are no illegal updates to that register or the page table entry, at least that particular field, and have that only come through this call gate. So we enhance the unikernel trusted computing base, and we prevent unwanted update or access to the PKA register or the page table entry of protected pages. Okay? So we provide this API for user functions to go through to make these updates. I'm going to skip through this detail of how that works. You can look at the paper. So I wanted to give you a little bit of a sales job of how good this is. Same application, and we said, let's look at how we can beat us our own work, which was what we had published 3 years ago, and said, can we actually, how much better are we for still providing this protection? Okay, we looked at actually 2 deployment settings. One is intra-node, just like we had done with SPRIGHT, And then we also went across nodes. And here we distributed these functions between a pair of nodes. Okay, so we looked at SPRIGHT. We were previously very proud of how we did compared to some of the other competition, including just plain KNative. And at that time, there was another competitor called Nightcore, and we were doing better, both in terms of requests per second, in terms of the latency distribution that you see, whether you go within one node or you go across nodes. But when you look at what happens when you resort to using this unikernel, we get an order of magnitude better performance, both in terms of RPS and in terms of latency as well. Even when you go across nodes, there's a dramatic improvement. And that comes at a significant benefit in terms of CPU utilization. We said, let's look at the CPU cost not in terms of pure CPU, but in terms of CPU cost per request per second. And, you know, lower CPU cost per RPS is what you want. And we look at the intra-node case and the inter-node case. And what you see is that compared to SPRIGHT, we're able to do better under certain circumstances and not that much better than SPRIGHT in other circumstances. So if you look at light load, what we're doing with Sure, with our unikernel approach, is we resorted to using, since we don't have a kernel, we resort to using DPDK and polling. So that ends up consuming a little more resources in Sure for small concurrency levels. But when you get to higher load, what happens is that that polling becomes so much more efficient, and that helps in bringing our CPU cost per RPS at higher loads much, much lower. So there's a significant benefit out of that. So I'm more or less done. I don't know how I'm doing on time, but you know, if you look at serverless, there are many things that are running all the time, and there's so much overhead. And the shared memory that we've been working on for so long streamlines that data plane for serverless, and using eBPF helped us to really go to being event-driven. And what we did with this unikernel framework was mimic that and do better, both in terms of startup. So we completely mitigate, not completely, we substantially mitigate this issue of cold start penalty once we get to this approach. And we really, using this MPG-based call gates, were able to have really fine-grained memory access management and protect our shared memory, and also all of the things that the cloud service provider trusts. And what we've done recently is to add to this going between nodes using RDMA rather than what we did here with ZStack. I'm done. I can take questions or...
Questions?
Well, good afternoon, Professor. This is Xinyang from HKUST, and thanks for talking. And
Your student?
Yeah. And I have a question about you know, the unikernel-based or lightweight serverless framework. And I wonder, how can we building a scheduling system over such a lightweight framework? For example, how do we cover the latency cost or something other cost at the data center level? Yeah.
So when you say scheduling, are you talking about placement?
Yeah, yeah. That is one type of the...
So I see that as a problem that it doesn't matter whether it's unikernel or containers, you still have to solve it.
Yeah.
And we did, in the past, look at the control plane. Much of this is data plane focused, But we looked at the control plane and we said, hey, we can actually do better in terms of placement than what things like Kubernetes does. And we said we can actually use much finer grained policies than using this coarse sampling that they do. They do it coarsely because they have to actually go and query the sidecar to get those metrics. And they don't want to actually have too much overhead for that. What we said instead is we can piggyback a bit of information every time a response comes. And that, if you can have a carefully constructed way of collecting those metrics, you can have a very fine-grained placement. You can deal with fairness, you can actually bring up the utilization more and so on. So we did that before we got started with these unikernels, but I think those approaches can still apply.
Okay, thank you.
So I want to ask, a lot of the work that you've been doing seems to follow along two different lines of rethinking the stack. One is functionality, recalibrating the functionality. The other one is about the trust boundary, redefining trust boundaries. So have you looked into whether there exists any opportunity to leverage more deeply a hardware software co-design? Perhaps one would be at the level of smart NICs that are getting more and more popular and programmable, whereby the definition of a trust boundary can also be associated closer to the infrastructure level.
Same thing. Some of these things that we say, once you move to RDMA, you need to be sure that you don't have user code have access to the networking infrastructure.
So have you looked into this already?
We've been doing this DPU work, and we submitted it to SIGCOMM. Those guys kicked us out, but
okay.
It's a small paper there, but we've sent it to Eurosys.
So it's coming.
We're very happy. We've put it out on archive as a paper as well.
Okay, thank you.
This is not ML. Why are you asking questions?
I want to ask about the PTE part.
Huh?
The PTE part, page table entry, with the key.
Huh.
How about the scalability? Because if there are 16
I feel that
keys,
that is
right?
exactly why we did this split, right? We said, hey, we want to worry about correctly securing key components, but we also want it to scale, right? So you can have a huge amount of shared memory, okay? You don't need to have huge pages that are multiple gigabytes, and you can now, the kind of access you want for the shared memory as you pass from one function to another is read-write to read-only. Potentially, occasionally you want it to disable access. And that's why we can directly update the page table entry. There is a price that I'm paying, which is flushing the TLB. That
Okay.
I wish I could do better.
Okay. I was just thinking if you have like hundreds or thousands of containers and 16 keys and...
So they can still reuse the same. How many different ways are you going to use that page? Read, write, or don't read, write. Okay. There's no other way, right? Okay. So that's all we are looking to use it for. You don't need multiple different keys. You need 3. Okay. And you can then keep updating the page table entry for those pages. All right. By just pointing to one of those 3 keys. And the rest of the keys you can use for what you need for finer grained, the coarse-grained access by having the other 12 or whatever keys that you have available.
Okay.
It scales.
Okay.
The scale problem is the TLB.
Okay.
Okay, thanks.
Yeah, KK will be sitting in the panel tomorrow afternoon. I know some of you in the audience working on like serverless computing and the eBPF. And if you have questions, you keep your question in the panel. Okay, you can ask them. Okay, let's thank KK again. All right.